The soil hydrometer test allows us to quantify fine-grained particles and their sizes. This is accomplished through a soil hydrometer. This is a picture of one, and it will be our primary tool used during the test. The soil hydrometer has a scale which indicates its suspended length. The suspended length gives us an idea of the percentage of fines that are in suspension when placed into a slurry mixture. The first step in the hydrometer analysis is to calibrate our hydrometer. Since manufacturers furnish standard hydrometers calibrated at 20 degrees Celsius and from the bottom of the meniscus, we must compute a composite correction factor. The composite correction factor accounts for deviations from the standard calibration that may occur during the test. Two types of hydrometers are available, the 151H and the 152H. Depending on which one we are using during the test, we must use one of the two equations to compute the composite correction factor. To calibrate our hydrometer, we must control as many variables as possible. This is accomplished by utilizing a solution with the exact concentration of dispersing agent. The soaking solution is deionized water containing a concentration of 40 grams of sodium hexametaphosphate per liter. The ASTM standard also states that the test slurry temperature must be between 16 degrees Celsius and 30 degrees Celsius. First, weigh out exactly 40 grams of granulated or powdered sodium hexametaphosphate and add it to 1,000 milliliters of deionized water. Stir or mix thoroughly. "125 milliliters of sodium hexametaphosphate solution is specified for sample soaking. Therefore, for calibration purposes, 125 milliliters of sodium hexametaphosphate solution is added to 875 milliliters of deionized water, totaling to 1,000 milliliters. Composite correction factor for a range of temperatures. The goal is to find the composite correction factor at the specified upper bound temperature, 30 degrees Celsius, and the lower bound temperature, 16 degrees Celsius. Then linearly interpolate composite correction factors from the lower bound to the upper bound and extrapolate a range of composite correction factors with an increment of 1 degree Celsius. This allows us to find a unique composite correction factor for our test slurry temperature. First, cool the calibration solution to a constant temperature of 16 degrees Celsius. Then carefully place the hydrometer in the cylinder and allow for stabilization. Read out the intersection of the scale on the hydrometer and the top of the meniscus. Perform the same operation, just this time with the temperature at a constant 30 degrees Celsius. The readings taken at each temperature is known as the composite correction factor, unique to that temperature. Since we do not know the exact test temperature, but know it will fall within a particular range, we linearly interpolate between the upper and lower bounds. This produces a chart similar to the one shown here. A graph or plot may also help extrapolate a composite correction factor for a unique temperature, with temperature on the x-axis and composite correction factor on the y-axis. The first step in sample preparation is selecting the amount of oven-dried sample to sieve. Refer to 5.1.1 of the ASTM standard. In our case, the sample nometer diameter of largest particles was less than or equal to 3/8 of an inch, so we used a 500 gram oven-dried sample. Next, sieve the sample over the number 10 sieve. Conduct sieving operations by means of lateral and vertical motion. Continuously keep the sample over the sieve. Mechanical means may also be used. Never manipulate fragments of soil by hand. The material retained on the number 10 sieve may be used for further analysis, i.e. shake analysis. Therefore, save this portion of the sample for later. The material passing the number 10 sieve must be visually classified. If the material is primarily a sand, use 100 grams for the hydrometer test. If the material is primarily a silt or a clay, use 50 grams for the test. In the case of our sample, it was primarily a sand, so we weighed 100 grams of the material that passed the number 10 sieve. This portion is now ready for soaking. We must take into account moisture content differences between air-dried and oven-dried samples. To do this, we must find and apply a hygroscopic moisture factor. Weigh out 10 to 20 grams of the original 500 gram sample and record this value. Oven dry the amount at 110 degrees Celsius. After drying, record the oven dry mass. Then the hygroscopic moisture factor is the proportion of oven dry mass to air dry mass. This factor is always less than 1. We will later apply this value in our data reduction section. The soaking period is 16 hours, so place the sample in a glass beaker and pour 125 milliliters of the 40 gram sodium hexametaphosphate per 1000 milliliter solution into the beaker. Cap the beaker and allow for soaking to take place. Sodium hexametaphosphate disperses the agglomerations within the sample, so that its true grain size may be determined. After 16 hours of soaking, the soaking period has ended. The test is now ready to begin. Remove the sample from the beaker into a dispersion cup with a squirt bottle. Be sure and remove all the residue. Next, fill the cup halfway with deionized water. Place the cup into an approved mixer with paddles that turn at 10,000 RPMs. Allow the sample to mix for exactly 1 minute. The mixer further disperses the sample. After exactly 1 minute, stop the mixer by simply removing the cup. Pour the slurry into an 1000 milliliter cylinder and again use a squirt bottle in doing so. Remove all residue associated with the dispersed sample. Fill the 1000 milliliter cylinder with deionized water. Fill to exactly 1000 milliliters and place a rubber stopper or the palm of your hand over the top of the cylinder and rotate as such. Rotation should take exactly 1 minute. A half rotation should take 1 second. Therefore, a full rotation should take approximately 2 seconds. Take the first hydrometer reading exactly 2 minutes after sedimentation. Be sure and place the hydrometer in the slurry 20 to 25 seconds before reading time. The reading is the intersection of the hydrometer scale and the top of the slurry meniscus. Record the actual reading. Also record the temperature of the slurry. Be sure and apply the composite correction factor to the actual reading. The corrected reading is simply the actual reading minus the composite correction factor. Recall that the composite correction factor is unique and depends on temperature. The reading times are listed here in chart format. Readings are taken at the spaced intervals relative to sedimentation time. Record the actual hydrometer reading, corrected hydrometer reading, and temperature for each of these times. After the last reading is taken, the total sedimentation time has been 24 hours. So take the last reading the day after sedimentation has begun. The slurry is not to be discarded, for further analysis may be performed. Recall that we saved the material that was retained on the number 10 sieve from our original 500 gram sample. Perform a shake analysis on this amount using the following nested sieve set: larger sieves on top and smaller sieves below. Transfer the retained amount to a bowl. Be sure and remove any clods or grains stuck between sieve openings. We can use a steel brush to do so. Pour the amount into the nested sieve set, place the lid on top, place the sieve set in a mechanical shaker, set the time to 15 minutes, and turn on. Tilt the shaker so that the sieves are rotated and hit the sides properly during the shaking period. After 15 minutes of shaking, remove the sieve set from the mechanical shaker. Weigh and record the amount that is retained on each sieve in a cumulative fashion. For example, weigh the amount on the 3-inch sieve and record that value. Then pour what was retained on the 2-inch sieve into the same bowl and record that value, and so on. This will later be used in a total assessment of the sample. Pour the hydrometer slurry over the number 200 sieve and wet sieve the material. Remove all soil grains from the cylinder using a squirt bottle. Washing removes all the silt and clay out from below the sieve. Wash until the wash water is completely clear. This is when you know that the retained amount is sand. The sand retained will be used for shake or grain size analysis. After the wash water is clear, pour the retained amount in a bowl and prepare to oven dry the washed soil. After the washed hydrometer material is dry, remove it from the oven. Allow soil and bowl to cool. Add the amount to that which passed the number 10 sieve, originally from our 500 gram sample. Now this is the total, ready for shake analysis under the prescribed sieve set. Again, pour the combined material into the nested sieve set. Shake the sieve set as we did previously. After the shake, weigh the amount retained on each sieve in a cumulative fashion. Our hydrometer worksheet should look something like this: the time in the left column, actual hydrometer reading next, temperature for each reading taken, composite correction factor, and finally, corrected hydrometer reading. A numerical value of 1 is added to the corrected hydrometer reading for the 151H. For example, let's look at the first row. 19 minus 1.5 is equal to 17.5. This rounds up to 18. Bring the decimal back 3 places and add 1 for a value of 1.018. This will later allow us to correctly calculate the percentage of soil particles in suspension, P. We must next compute the oven dry mass of soil relative to the hydrometer test. W is equal to the hygroscopic moisture factor times the mass of the air-dried sample used for the hydrometer test. Our hygroscopic moisture content was 0.994 times 100 grams of our air-dried hydrometer sample from the beginning is equal to 99.4 grams. This is our oven dry mass of soil. With W, the oven dry mass relative to the hydrometer test, we must calculate the percentage of soil particles in suspension for each hydrometer reading. A unique equation is used for the 151H and the 152H as shown here. G in the 151H equation is the assumed specific gravity of solid particles, normally a value between 2.6 and 2.75. G1 is the specific gravity of the liquid in which the particles are suspended. R is the corrected hydrometer reading. A in the second equation for the 152H is the correction factor for the assumed specific gravity of solid particles found in Table 1 of the ASTM standard. Next, we must use Table 2 of the ASTM standard. Table 2 establishes effective depths based on actual hydrometer readings. Each hydrometer reading will have a unique value of effective depth of the hydrometer. Be sure and use the actual hydrometer reading when extrapolating the value of L. Once we have unique L values for each hydrometer reading, the diameter of soil particles corresponding to the percentage of soil particles in suspension can now be calculated. Each hydrometer reading will have a unique value D. D is equal to K times the square root of L over T in units of millimeters. K is equal to the constant that depends upon the assumed specific gravity of solid particles and temperature of the slurry. Table 3 establishes this relationship. T is equal to the time the reading is taken from sedimentation. Again, notice that D is in units of millimeters, and this will later be used. Here's our modified chart. We have corrected hydrometer reading on the left-hand side column, percentage of soil remaining in suspension, K value, L value, the effective depth of hydrometer, D, the diameter of soil particles in millimeters. Notice that there is a unique value for each hydrometer reading of P, K, L, and D. Now moving on to the coarse grain analysis. We can calculate the percent passing relative to the shake analysis. Recall that our original sample size was 500 grams air-dried soil. The weight retained on each sieve should be recorded in a cumulative fashion, W retained. The weight passing that sieve can be calculated W passing, which is the total sample minus the weight retained in a cumulative manner. The percent passing each sieve can now be calculated P passing. That is W passing divided by the total sample weight, which is 500 grams in our case, times 100%. We'll have a unique percent passing for each sieve. Here's a typical coarse grain analysis worksheet. The sieve designation in the far left-hand side column. The sieve size is next in units of millimeters. Then the weight retained on each sieve. The next column is calculated by subtracting the total original sample weight from the weight retained column, giving us weight passing. Finally, the last column is calculated by dividing the weight passing by the total sample weight. Notice that the total sample weight here in this calculation is 490 grams. for we used 10 grams to obtain a hygroscopic moisture from our original 500 gram sample. To go over the calculation, we will look at the first row. 3 grams was retained on the number 4 sieve. Nothing was retained on sieves larger than this size during our test. 490 grams minus 3 grams is 487 grams, which is the total weight of the sample that passed the number 4. Next, 487 divided by 490 gives us 99.38%. Therefore, 99.38% of our sample passed the number 4 sieve. The calculation continues in the same manner for every row until the number 200 sieve. The number 200 sieve is the brink point that discerns sand from silt and clay. So everything between the number 4 sieve and number 200 sieve is considered sand. Everything that passes the number 200 sieve is considered silt or clay. This chart displays the combination of coarse grain analyses and fine grain or hydrometer analyses. Notice that the number 200 sieve is 0.075 millimeters, and that everything below this point in the chart is taken from the hydrometer analysis. The diameter size D in the left-hand side column, and the percentage of soil in suspension, or percent passing, in the right-hand side column. This means that everything in suspension after sedimentation is considered to pass the number 200 sieve, and is classified as silt or clay. The combination of coarse grain and fine grain analyses gives us the total distribution of grain diameters for the soil tested. Here is the combination of analyses in plot format. The y-axis is percent passing, and the x-axis is grain size diameter in units of millimeters. Notice that the x-axis is on a log scale, giving us a semi-log plot. The semi-log plot allows us to extrapolate grain diameters easily. Notice that the brink points are displayed on the x-axis in red. This allows us to retrieve total percentages of gravel, sand, and silt or clay relative to our sample. Next, notice the black lines at 60% passing, 30% passing, and 10% passing. These are important values in geotechnical engineering known as D60, D30, and D10, respectively. The diameter of soil grains at which 60% is finer and 40% is coarser is known as D60. D30 and D10 have a similar definition. These values allow us to calculate coefficients which will further classify the sample. This is a typical plot of a soil sample classified as silty clay sand trace gravel by the Unified Soil Classification System. Coefficients of uniformity and curvature. These two coefficients allow us to further classify the soil from its gradation, specifically allowing us to define its grade. Cu is equal to D60 divided by D10. Cc is equal to D30 squared divided by D60 times D10. If Cu is less than 2, then the soil is defined as uniformly graded. This means the grain diameters are uniformly distributed relative to one another. If Cc is between the values of 1 and 3, then the soil is well graded, meaning it possesses many different grain sizes. If Cc is greater than 4, then the soil is poorly graded and does not contain a variety of grain sizes. Keep in mind Cc is a measure of the curvature of the previous graph displayed. We will now compute Cu and Cc for our test soil. From our previous semi-log plot of percent passing versus grain size diameter, we extrapolated the values of D60, D30, and D10 listed here. Now we apply the given equations and obtain a Cu value of 142.8 and a Cc value of 3.6. This means that our soil is non-uniform and well to medium in grade. This concludes the coarse and fine grain test procedures and data reduction.